Okay, let's talk more about perspective. Remember when we started off, we had that viewer, and he was 6 feet tall. Well, now let's assume that we're viewing him from the top view, right? Top view. And here he is. He's got his two eyeballs. And for our purposes, let's assume that the start of his view is right there. And just like last time, it was his line of sight. You all remember the line of sight? What goes infinitely out like a blast from Cyclops of the X-Men. And for our conjecture, in which Cyclops is locked in a paralysis by Magneto or something, this is perpendicular, or it's also parallel to the ground. It's a top view, so we don't really care about that. Now, let's say we had a line, just for conjecture, that was exactly perpendicular to this. Make it really small. And this is mostly just interesting because we care that it's going to be 90 degrees here for this angle. And now let's also assume that we have just a row of identical planks. So let's just let's make them a nice green color, perhaps. And I'm going to try and make this exactly in the center. Something like there. And perhaps there's one there. One over here. They don't have to be perfectly spaced. Because right now we just want to see the rays that get generated from this as they approach our eyeball. Way over here, we have our last two, right? So let's start over here with our first one. How do these rays approach the eyeball? Note that as they go from there to there, this is a pretty extreme angle. And in fact, if we go down here, I'm going to make this a little wider. So how about now? You'll notice that this is not a big line, right? This is about 6 foot tall. This is like if you laid this guy on his side and he was 6 foot tall, that's about how long this is. So it's about the size of a sidewalk. And yet when it's really close to him, like there, before I draw that, notice how when it's this really close one, it's practically parallel, or it's practically perpendicular to our line of sight. It's that 90-degree angle because it's so close to us. And essentially what happens is as things get really, really close to our vision, they get extremely distorted. Now what happens on the opposite end? Well, this is not a big distance to travel. This is less than, this is probably like 20 feet, 30 feet. And yet notice what's happening out here. Let's say we extend that a little. Extend that a little. Something out here. Again, not a large distance to travel. This is about 50 feet, maybe. And yet already we're seeing something kind of crazy. Whereas previously we had a perpendicular angle to the ground, to the line of sight, now we have lines that are practically parallel to it. See those two lines? Here's our line of sight, parallel. Here's the ray getting generated from whatever's over here, practically parallel to it. So what does this mean for us in practical terms? Well, imagine, I'll do those crops. Well, now we're going to draw our first perspective grid. Imagine you have a straight line for your horizon. And I want to turn my grid on so I can see this. So this is my horizon. And again, it's where we see that curvature of the Earth. And we just can't see anything else. So here's us standing on the ground. Our line of sight goes out. Eventually the Earth's curve means we have nothing else to see. And our line of sight keeps going. The Earth does not. And right here in the center is our principal vanishing point. Now what distinguishes the principal vanishing point, or PVP? It's a lot of the angles that come off of it. Again, we're assuming that we're Cyclops. Here's Cyclops. And this line coming out is going to travel in a perfect straight line forever. It's always going to be in the direction you're looking, but we're also assuming that Cyclops is standing very still. He's looking straight out. He's parallel to the ground. And so that's important. In other words, we're dealing with 0-degree angles, where this is 0 degrees from the ground to this. They're exactly parallel. And also we're dealing with things that are 90 degrees. In other words, directly opposed to those two. Now what happens is when you have that line of boards or whatever that were sitting on the ground there, the sidewalk. I'm going to start by just drawing a single one of them. And you'll note that I'm trying to put this equidistant on both sides of the principal vanishing point, as if, again, to make our life easier, we're assuming that Cyclops here is standing in the direct middle of the sidewalk, and therefore his line of sight travels directly down it. The same amount of distance on this side of the sidewalk as there is on this side. So what happens is all of our lines on the ground that we drew from that top view are going to converge at this principal vanishing point. Because, as we saw, when we start off, we have this extreme angle, and this first one, way over here, where we were like this, we probably would not even be able to see that. And with this one, we're still getting a pretty extreme angle. This is probably that first one I'm drawing, where it's taking up a lot of the ground view. But the further out, that angle and the amount of extremity it has is going to get less and less. So we can now see this. If I assume that all those posts are the same, they're all going to appear on this, between these two lines. And again, remember, I was not making any mathematical conjecture. But we're also going to see something, which is as they get closer to the horizon, they're going to get closer and closer together. Until eventually, way down here, they'll practically appear to be on top of each other. Pretty neat, right? Now what if we wanted to make these actually perfect? As if these lines on the ground appeared every 10 feet. And they're always the same length. They're always 6 feet across. Well, for that, we're going to have to get into the next arena, which is secondary vanishing points.